Hello, this is video number 5 on my single variable calculus 2. In this video, we're going to talk about parametrized curves. A parametrization for a curve C on the xy plane is a way of writing down x and y as a function of a parameter. Think about a curve in the two-dimensional space, and in fact we can do the same thing in the three-dimensional space as well. Now, not all curves are graphs of functions, so a curve like this doesn't pass the vertical line test, but we can think about this one as the trajectory of a particle. So at any time t, we have an x coordinate and we have a y coordinate that we can say these two are functions of t. So maybe I'll just use the same notation that I have in this example. So x coordinate is f of t and y coordinate is g of t. So this is called a parametrized curve, and f of t, g of t are called parametrization of this curve. So most of the examples are going to look like either you're given a parametrization and you're trying to sketch the graph of that parametrization, or you are given a curve and you're asked to find a parametrization for that curve. So let's look at an example. Sketch the curve given by this parametrization. So first thing we're going to do is we're going to find the parameters. So t from the first equation is x minus 1. Then we can plug it into the next equation. So we get x minus 1 squared minus 1. This is a parabola. Vertex is 1, negative 1. So if you plug in x equals 1, we get x squared, x minus 1 squared equals 0. So the parabola looks like this. 1, negative 1. That's the vertex, and it's opening up because the coefficient of x squared is positive. Now let's find the intercepts. We get x minus 1 squared minus 1 equals 0. This gives us x minus 1 equals plus or minus 1. So that gives us x equals 0 and 2. So at x equals 0 and at x equals 2, it intersects the x-axis. Now they also told us that t is between negative 1 and 2. So let's figure out what the values of x and y are for x equals negative 1 and 2. For x equals negative 1, we get 0. For t equals negative 1, we get 0 for x and 0 for y. For t equals 2, we get x equals 3 and y equals 2 squared minus 1, which is 3. So at x equals 3, we get y is 3 as well. So those are going to be the endpoints of this curve, this point, and it's a parabola, so it looks like this. Now, in some instances, they ask you to indicate um, the direction in which the curve is traversed as t increases. And if they did that, then you would have to put the arrow this way because this is for t equals negative 1 and this is for t equals 2. In this case, they didn't ask us to indicate the direction by an arrow, so we're going to leave it at that. Okay, so we'll do a few more examples on this. The next example, I'm going to do two examples here, is find the parametrization for each of the following curves. The first one is the circle of radius r centered at the origin. So let's draw a diagram for this one. We have a radius, a circle of radius r, and we want to find the parametrization. So if we measure this angle, we can write down the parametrization using this angle. If you look at this angle, I'm going to call that angle t. We can find the x coordinate and the y coordinate using this t and the radius. So if you look at this radius, this triangle, we have sine of t is opposite. Opposite is right here, which is y, divided by hypotenuse. And cosine of t is adjacent, which is x, divided by hypotenuse. So that tells us that x is equal to r cosine of t and y is equal to r sine of t. And this parametrization must come along with the limits of the parameter, and this is part A. So what are the limits of t? If we want to traverse the circle once, then the limits of t would be from 0 to 2 pi. Next part of the problem is find a parametrization for the circle of radius 5 centered at 2, 3. So it's very similar to the previous one, except the center is a different point. Now there are a couple of different ways of thinking about this one. So 2, 3, so this is our center, and the radius is 5. So something like this. So this is 2, 3, and the radius is 5. There are two different ways of writing down the parametrization. I'm going to write down two different methods. So method number one would be to think about it this way. Well, what if this were a circle of radius 5 centered at the origin? If it were centered at the origin, then based on what we just saw, it would be 5 cosine t and 5 sine t. So this is a circle centered at the origin with radius 5. But we are moving the origin, which is 0, 0, to 2, 3. It means we are increasing the x component by 2, and we are increasing the y component by 3. So the parametrization then becomes the same as the parametrization of a circle of radius 5 centered at the origin, except x and y are increased by 2 and 3. The second method, which some students may like this method better, is to write down the equation first. So equation is x minus 2 squared plus y minus 3 squared equals 5 squared. This is the equation of the circle of radius 5 centered at 2, 3. Then we can write this down as x minus 2 over 5 squared plus y minus 3 over 5 squared equals 1. Now we know that cosine squared plus sine squared is 1. In other words, x minus 2 over 5, y minus 3 over 5 lies on the unit circle. In other words, we can write this down as x minus 2 over 5 equals cosine of t, y minus 3 over 5 equals sine of t. And of course, t is between 0 and 2 pi. And that gives us the same parametrization. So we get 3 plus 5 cosine of t, and we get y equals 2 plus, or rather this one is 2 and this one is 3 plus 5 sine of t, and t has the same range of 0 and 2 pi. So this would be our parametrization. Okay, let's look at the next example. Find the parametrization for the line segment starting at 2, 1 at time t equals 0. So we have 2, 1 and ending at 1, 2. So 1, 2 is right here. So this is the line segment. So it starts at 2, 1 for t equals 0 and ends at 1, 2 at t equals 1. Well, first of all, this is a line segment. Because it's line segment, you would expect the parametrization to be linear. So it would have to be something like a plus bt. It's a linear parametrization. At t equals 0, we have to get 2, 1. So it would have to be 2 plus at and 1 plus bt, because it's a line, and because at t equals 0, we would like to get 2, 1. So this would have to be the parametrization. Now, let's look at what happens at t equals 1. So we want at t equals 1 to get 1, 2. So x would be 2 plus a, and y would be 1 plus b. We would like this to be 1. This comes from here. 1, 2. So this is the equality that we want. And then we solve this one for a. So a becomes -1 and b becomes 2. So the parametrization is going to be x equals 2 minus t and y equals 1 plus t, and t ranges from 0 to 1. And we can test this. We can check if this is in fact this in fact does give us the points. If you plug in t equals 0, we get 2 comma 1. If you plug in t equals 1, we get 1 comma 2. So let's look at one more example, and this is the last example that we do, and then we will summarize. Parameterize the ellipse given by that. So we're going to draw the ellipse. This is the x-coordinate, x-axis, y-axis, and this is a, b, negative a, negative b. So that's an ellipse. The center is the origin, and we want to figure out what is the parametrization of that. So it's a very similar equation to a circle. The only difference is we have constants here. So think about it this way. If you think about it this way, then this a x over a and y over b are points on the unit circle. In other words, we can say x over a is cosine of t and y over b is sine of t. And of course, because it's a full ellipse, t would be between 0 and 2 pi. If it were a quarter of an ellipse, it would be between 0 and pi over 2. If it were half of the ellipse, let's say the upper half of the ellipse, it would be between 0 and pi. So that gives us the parametrization as x equals a cosine of t, y equals b sine t, and t is between 0 and 2 pi. And that is the final answer to the problem. So to summarize, what we learned in this video is that to parameterize a curve, we need to write x and y in terms of a variable t. Each parameterization must indicate the limits of the parameter. So look at all of the parameterizations that we did. We indicated the limits of t, and it would always have to be indicated what the limit of t is. Even if t is all real numbers, you would still need to indicate the limits of t. To identify a parameterized curve, find a relation between x and y. The first example that we did was like that. And then sketch the curve given by the relation, and then check the limits of the parameter and make sure only select the portion of the curve given by the indicated values of the parameter. If you look at a circle of radius r centered at x0, y0, a circle of radius r equation is centered at the origin would be r cosine r sine. This would give us a circle of radius r centered at the origin. If the center is x0, y0, we add x0, y0 to x and y coordinates. And of course, because it's a full circle, t would be between 0 and 2 pi. If it is an ellipse, then we have to do a cosine b sine x minus x naught over a would have to be cosine t, y minus y naught over b would have to be sine t. And once you put the center at x0, y0, you'd have to add x0 and y0, and of course t is between 0 and 2 pi. And that brings me to the end of this video. So I will see you in the next video.